when we're talking about inorganics, let's highlight these things so we can see what's going on. So this is 8.1. So I'm going to use blue to separate the different units out for you. So there's, oh, wait a minute, what's going on here? Yeah. And so I think what I'm going to do actually is I'm going to go through and see where 8.2 is. Let me see now. 8.2 is way down on page 7. And this topic is about Lewis diagrams. Okay, so at 8.2. Is there even an 8.3? 8.3, organic chemistry. So these are meant to be color flags showing separation of the different units. And I think that's it. So now the subheadings I'm going to use, how do I say this? Not for subheadings, but for things that are kind of like definitions, I tend to use orange. So inorganic molecular compounds, thank you. Inorganic molecular compounds, these are from abiotic sources. Abiotic means non-living. I'm sure that was shared with you in previous courses. From abiotic sources. So basically minerals, really. They are generally metals bonded with nonmetals or two nonmetals. And we have some examples here. We have, yeah. Oh, sure. Thank you. Okay. So we've run into these guys already. Sulfur trioxide, phosphorus trichloride, dinitrogen trioxide. These are all metals, nonmetals and nonmetals, okay? Oh, I missed something. Sorry. I'm reading down a line. This is with two nonmetals. Inorganic ionics. They're the ones with metals and nonmetals. So they are from abiotic sources. Non-living sources. They are metals who have lost an electron, and a nonmetal who has gained an electron, or involving polyatomic ions.
Move it up. I can't see.
Sure, thanks, dear. Keep on me, eh?
I suppose when.
Okay, where we are.
Sorry.
No, don't be sorry, dear. Where are we?
Oh, whoops.
It's just my bad writing. Or involving polyatomic ions. Okay?
What does it say right above after non-metal?
Right here.
Right after non-metal? Like right after a line?
Gains an electron. Non-metals gain the electron. Metals lose an electron. Or if they involve polyatomic ions, either way.
Okay, thank you.
No problem. No, please don't be sorry, dearie.
What's in bracket?
lose an electron. I'll try to write better, I promise. So we have some examples here. HCl, metal and a non-metal. Calcium nitrate, metal and a polyion. Copper 2 phosphate. Multivalent metal, polyion. Organic compounds. These are compounds that are derived from biotic or living sources. Not that they're living now, but they could have been alive a very, very long time ago. Okay. How can you tell if you've got an organic or not? They have a high carbon content. Sometimes in the form of a backbone. For example, right next door here, there is a picture of this is this is glucose. Yeah.
Can you move it up? And
Sure.
does that say backbone?
Yes, it says backbone.
Backbone, yeah.
Not backbone.
Yeah. So, for example, here is the carbon backbone in this chain configuration of glucose. Both of these are glucose molecules. The other chain is here. It's inside. It's this. That's the other chain. But this chain just happens to form a complete circle. But it's still a backbone. Okay? Other things that you want to look for. So high carbon content is a must. It has to have a high carbon content. It will also be high in hydrogen. As you can see from these two diagrams, we've got hydrogens all over the place all day. And to a lesser degree, oxygen. So the moral of the story here is for it to be organic, it has to have carbon and hydrogen, but it doesn't actually have to have oxygen. It can or it might not. Often it does, but not always. So this one here, I'm just going to put, well, sometimes. Not all the time, just sometimes. Yes, sir.
Wait, does not what? So it says why fossil fuel or coal are considered non-organic?
Because they were once alive. They're considered organic because they're once alive.
Oh, so even if it's organic, doesn't mean.
No, as a matter of fact, within living systems they are, but not in. If a system is dead now, it's that's it. You're done. Okay, good question. And these are all molecularly bonded. They're all molecularly bonded, which means they share electrons. Okay, so that means they're like holding hands doubly. They don't want to let go, so it's hard to split these guys apart. So here's probably this one here, CH4. That's methane. That is the simplest organic compound around. Okay, so you can see that if you C, it would look like this, C, and it's going to have 4 H's hanging off it. So that is as simple as it gets. We've already looked at glucose, which is here. This one here, you've seen this before. This is not new to you. This is acetic acid. Okay? If I take the H off, and I instead put a sodium on it, this is still an organic molecule because it has a carbon backbone, it has hydrogens, and that is what checks the box that this is actually organic. The fact that it has a sodium has nothing to do with it. One that is you're probably very familiar with is this. This is what we put in our vehicles to make them run. Gasoline is a mixture of different chemicals, but the majority of the gasoline is this thing here. It's called octane. And so if I was to draw octane, I'm just drawing this out to make the point that it has a long carbon backbone. Yep. So some of you are looking at this saying, okay, Mr. Hayden, you must have told us a lie because I don't see any carbons in that. The carbons live wherever there is an end point or where there's a bend. So if you count these up, you'll see that there are 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. If you count the hydrogens, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, octane. Okay? So, moral of the story, take-home message from this part is that you've got to look for the carbon. Now, there's some things that you're going to look at and you're going to say, wow, not sure if that's organic or inorganic. For example, if you said, if I gave you CO2, you would say, whoa, wait a minute, that's got a carbon, so that's the first checkbox. It's got oxygen, but I missed the second checkbox. The second checkbox has to have hydrogen, so this could not be organic, even though organic entities produce it. Like right now, you're producing carbon dioxide. It itself is not an organic molecule. Okay? Yeah. Did you have a question? No? Everybody's good? Okay. That's it for the introduction to carbon chemistry. We'll pick it up a little bit later when we talk about carbon molecules later on. But I just wanted to start it off in there. What I want to do now is I want to look at acids, bases, and salts. So this is, we're talking about organic compounds. So now we're talking about acids, bases, and salts.
Can you please zoom out?
Yes, I will. Thank you, dear. And these are also of the inorganic nature. Most of them are. You're going to run into some organic acids at some point in your life. When I play with acids and bases, I always do this. The acidic part is red. There's a reason for that. It turns out that there's an indicator called red litmus, or litmus paper, and acid turns litmus red. Okay. The other thing I use is blue, which stands for base. And if you get mixed up, think of B for blue, B for base. Okay? Other colors I will use just to separate them from those two. Okay? So here we have a chemical reaction where we have, does anybody know what that is? Very good. This is hydrochloric acid, so I'm just going to write that down. Okay? This guy here, from your naming, you should be able to name this guy now. What's this guy? Very good. Very good. This is sodium hydroxide. Yes, certainly. So this is sodium hydroxide. And every lover of French fries identifies this guy, right? Yeah, or what do we call him? No, the chemical name. Very good. Sodium chloride. Okay. What do you think this is? Well, duh. It's water, right? Now there's a reason why I split this out in HOH, and my colors are going to tell me why, okay? So remember I said everything that is colored pink or red means acid. So here's, I'm going to color the H part because that is what makes hydrochloric acid an acid in the first place, is the H. Okay? I need to pick another color that is not blue, so I'm going to use green, just because. So here's green for the chloride. Okay? Base is blue, right? Hydroxide is blue, right? So I'm going to color this blue. And I need another color. Okay, orange will do. It's going to have to do. It's the only one I got left. So sodium is going to be orange. Now, you guys remember from your naming that the first thing that was up was the metal, and this is the thing that had a combining capacity of +1, right? So, or positive. So this is positive, and this is negative. The sodium, remember +1 for sodium, if you look at your periodic table, is +1. Hydroxide, if you look at your polyion table, is -1. Now, what do we know? What do we know about two things that have different charges? They're attracted to each other, right? If I have two positive charges, they're going to repel each other. If I have two negative charges, they're going to repel each other. Okay? So this reaction is a given, because what I'm doing is I'm taking the positive of this guy and marrying him to the negative of this guy, the positive of this guy, and the negative of this guy. Okay, so finish your color coding. So here we go. Na. Okay, so there's Na. Cl was green. Okay. And the first H, I'm going to arbitrarily name it the acidic H, and the OH, arbitrarily, this is the basic part of this, and so this is water. Okay? Is everybody okay? Now, a few definitions. You have an acid. So here is, you know what, I need to erase these pluses and minuses. Sorry about that. Okay. So this we've already figured out. This is an acid. This is, let me rephrase that. This is an acid. This is a base. And this is a salt. Okay? Now, you and I know this is the same salt that we put on our French fries, right? but it is not the only thing that we call a salt. Okay? The definition of a salt, in fact, is whatever is produced by an acid-base reaction. That is its actual definition, at least for grade 10. When you get into Chem 11 or Chem 12, we're going to talk about two other theories. Okay, so let's go down one step. Anybody know what this is?
Hydrogen hydroxide?
Close.
Dihydrogen.
What is the name of the polyatomic ion? Yes. This is hydrogen sulfate. Okay, but we call it, there's a street term for this. Okay, this is called sulfuric acid. This is nasty. This is the stuff that is in your car batteries that you do not want to get on your hands ever. This is sulfuric acid. Okay, going back to your naming. How would I name this? Yes.
Oxygen hydroxide.
Okay, you don't even have to put the oxygen because if you look at your polyonic table, it says hydroxide.
Calcium hydroxide.
Very good. This is calcium hydroxide. Now, got to remember to put E's on the end of my hydroxide, right? Okay. What is this called? What's the name of the ion?
Calcium sulfate.
Very good. This is calcium sulfate. Yeah. Calcium sulfate. Fate. And of course, now we've got water, right? So let's color code the actual species the same way, okay? So we can see what's going on here. So the hydrogens are going to be pink. I'm just going to go back and forth. So there's the first hydrogen. Hydrogens are taken care of. Hydroxides are here. Okay. Are you okay? Okay. Good. Hydroxide's here. The other is there. We're going to make calcium the orange guy. And so we see him coming to the other side, joined with the sulfate ion. So there we go. And last but not least, the sulfate ion. So here's the sulfate ion. And there. Okay? We good? Okay, so we have a calcium sulfate, right? It is the product of an acid-base reaction. What do we call this guy? A salt. Yeah. Okay. So if when you hear the word a salt, please do not let your brain go to sodium chloride, calcium bromide, calcium chloride, anything that is really a combination or can be made from an acid-base reaction, that is called a salt. A salt with a deadly weapon. Okay? Okay, a few more terms to look at. And then we're gonna do a little bit of doodling at the bottom of the page because I want to bring this home to another level. Aqueous and salts are two definitions here, so I'm going to do those in orange. Aqueous, does anybody here take Spanish? Or does everybody here take Spanish? Some of you take Spanish.
Oh, I
Yes, dear. You take Spanish.
Yeah, I thought you did.
Well, there's one that really takes Spanish. What is Spanish for water? Agua, right? In Latin, that's aqua. When we talk about aquamarine, it's referring to the water type of blue color, okay? So this means when something is dissolved in water. So aqueous means when something is dissolved in water. And as we already mentioned, that salt is the product formed by the reaction of an acid. Certainly. Up. Is that too much, or zoom out a little bit?
Yeah.
Okay. Of an acid and a base. Okay, let's do a little bit of doodling down below here. Yeah.
So under UHO, what do we put there?
This is the same. HOH is a long version of writing water. It's a long version of that. So this is just water. Thank you. So what do we know? What do we know about acids, bases, and salts? So I like to use tables for some of us who are better suited to that. So acids, and so I'm going to do this in red, just again the visual. Acids. So these guys release H plus ions in solution. So if you dissolve an acid in water, you are going to get these. We're going to get those. Oh, sorry, thank you. You are going to get H plus ions. Okay? Bases, again, I'm going to do those in blue. Frankly, I don't know if you can actually see the blue, so maybe where the word is. Okay? So bases, if you dissolve them in water, they'll produce hydroxide ions. And salts, they will not release either of those, but they will release two ions. One of them is going to be positive, one of them is going to be negative. So if you look at, say, if I take sodium chloride and I dissolve it in water, certainly it's going to produce sodium ions and chloride ions. If I take a base, say sodium hydroxide, and I dissolve this in water, it's going to produce sodium ions and hydroxide ions. Are you? I'm sorry? Here?
Yeah.
NaOH. And you guys probably jumped to the head of the this table here and said, okay, if I take an acid and I dissolve it in water, I'm going to get H plus ions plus chloride ions. Okay, so that's why I say acids, when dissolved in water, will produce H plus ions, bases will produce hydroxide ions, and salts will produce two that are not H plus and they're not OH, but they're something else. Okay, we good with that? Okay, other things that are interesting. First one is that all of these, if you run an electric current through them, they'll all conduct electricity really nicely. So I'm going to just write straight across conducts electricity well. Okay? Okay, going to do a sidebar here. Okay, so here we have water. And here is it's an organic acid. It's called bromphymol blue. It's not that good. Okay, now what you should be able to see that there's a slightly blue tinge, right? I'm also going to add a second indicator in. Oh, I can't find some. Here. Yeah. Yeah. They're very dilute though. So this is another one called phenolphthalein, and it is okay. So that's that. And I've got some a source of acid and a source of base. This one here. Okay. You see that? This is acid, hydrochloric acid, okay? And somewhere here. And this one here, it's hard to say, but it's rubbed out, but this is potassium hydroxide. So check out what happens when I add a few drops of hydrochloric acid. What happened? Change to what? To yellow. Okay? If I add a little bit of base, okay, it's gone back to blue. Okay? Now, we'll look at indicators, probably not today, probably tomorrow a little bit more. But if I continue to add a little bit of base, one drop, see what happens. It goes kind of more deep blue, more towards purpley, and then one more. Now I can play with this literally all day. If I wanted to push it back towards the yellow, I just add some acid. You would not believe how wonderful this magic is to grade ones. Seriously, Mrs. Gom comes up to their kids and they're just like,
Do they ask, like, do you do that
oh, you're magical. No, this is chemistry, okay? So, we'll talk a little bit more about that tomorrow, but I wanted just to kind of like whet your appetite with that today. So, what are other things that occurs? The first thing that we saw just now is that the acid and the base will cause color changes in indicators. Notice how I stop at this line here. Because a salt does not produce hydroxide ions or acidic ions, it will not react. It will not cause any color change. It will remain neutral, as a matter of fact. Okay? So the easiest way to say this is not does not cause color change. Okay? The other thing that you probably know about already is that there are certain soft metals that if you add an acid to, it will dissolve the acid and it will produce hydrogen gas. Like we'll do this tomorrow, I think. Magnesium and zinc react really vigorously to acid, and they'll produce gases for us, okay? So it's not all metals, it's just a few. So reacts with some metals to produce hydrogen gas. Remember, hydrogen is diatomic, right? Okay. Bases do not. So these guys don't. Not. Reacts with some metals
Okay.
to produce hydrogen, H2. Okay? Good. And finally, not. Okay, I want to clue you into a reason why this guy works. Okay, and this is what I wanted to point you in the direction of. In fact, the point of this is that water has properties of both an acid and a base simultaneously. Okay? The arrows mean that water can, we call this self-ionization. It can produce hydrogen and hydroxide ions by itself, and you don't need to do anything with it. But those hydrogen and hydroxide ions, because they're positively charged, can also join back to produce water again. And this happens all the time. As a matter of fact, if you were to take a glass of water, and I asked you, what is in that glass of water? Everybody's going to say, because we're in our second chapter of chemistry, everybody say, well, Mr. Hayden, that's H2O. And you'd be partly right. It turns out that there's also some of this in there, and there's some of this in there, but it is such a small amount, and they are even. There's the same amount of hydrogen ions and the same amount of hydroxide ions, so they balance out, so we don't see it. How little does it go? Now you get it that this is a really small number, right? It's like 0.000001. Okay. Yeah. Which way do you want it? This way? Oh, that's in the way. Okay, sure. I'm going to do, yeah. Actually, nothing, because there's such a little variation. Well, you don't want to, okay, you don't want to drink it because it's got the indicator in it. Indicators are not good for you. But so far as the acid and the base, it's so little that mostly this is now salt water. How do I know it's salt water? Because I put sodium hydroxide in, and I put hydrochloric acid in. It would taste salt. It would taste like salt water. Yeah, sir. No, you're not going to drink it.
No, I was just saying that all the salt probably.
Craving fries now. Sorry about that, bro. Okay, salts. The last thing I wanted to do was just to color in this green, because green is the color that I use when we're talking about salts, just so that we have the visual on that. Are we good? Let's mosey along to the other page, if that's to be the case. You are going to be given a pH scale handout next day, I think. But just to simplify things, I want to sort of like color this up a bit. First of all, pH scale, so this is a new topic. There we go, pH scale. Oh, sorry, pH scale. pH actually has there's a reason why it's called pH. What it means is potential of hydrogen, okay? And it is just a measurement of the hydrogen ion concentration. So, you guys haven't studied logarithms, have you? Not logarithms? 10 to the, not yet really. Okay, so what you want to think about this, you want to think of this as a reverse scale. What I mean by that is that the smaller the number, smaller the pH number, I'm sorry, the pH number, the more acidic the solution. Okay? So here, oops, should have an N on the end of that. Okay, good. Are we good so far? Okay. Not quite? While you're waiting, if you have a ruler handy, this is where they come in a bit helpful. Down?
Like sideways.
This way? Or down this way?
We just can see the
Oh, the more acidic the solution. Okay. So what I'm going to do is I am going to, boy, that's hard to see, isn't it? Somewhere out in this Never Never Land, didn't reproduce really well. Somewhere there. So this is meant to be a box. So this is a box. And there. And there. Okay? So if you draw that box, and then it doesn't really matter, I'm going to do it this way. I'm going to draw a diagonal from the top left-hand corner to the bottom right-hand corner. So, okay. We'll come back to this again on tomorrow, but acid we do pink, base we do blue, right? So if you have something that it has a pH of 0, you are pretty much 100% acid, okay? And as you substitute for hydroxide, you get less and less acid and less and less hydrogen ions and more hydroxide ions, such that, I'm not going to color it in, I'm just going to highlight it. So, and so going the other direction, if you have a pH of 14, you're pretty much 100% hydroxide. Okay? So, so you can see, right? Okay, this is the last thought, and I'll release you. The last thought here is that when something has an equal amount of alkali and an equal amount of acid, it is neutral. Or if you want to put it this way, if it has an equal number of H plus ions and an equal number of hydroxide ions, it is neutral. And it falls right there, pure water, which has a concentration of both of these at 10 to the minus 7, and therefore a pH of 7. Okay, let me go away. Chairs up, please. Scraps, please. See you tomorrow. There is, no, don't bother. I was going to say there is a homework sheet, pH scale. I think we'll wait until tomorrow for that. I can't print anything. I don't have, yeah, what they did is they updated the software on that machine in there, and now my computer can't talk to that computer.
Is it all filled up?
Pretty much. What do you need?
It's like 4 things.
Just let me get a piece of paper. I'm not gonna find it. If you just write down what you need on here, and I can even email it to you because I've got it in my drive.
I did pass the test, but I don't have it by mark. Much normally I get higher, so can I still attend the test? Okay, cool.
I don't care if someone gets 100%. It's nowhere near 100% either way. Yeah, we'll challenge you more about that and more just try to get numbers. Here's what I want to do.
Why is he so cute? It's not fair. Look at him. Look at him. It's not fair. Look at his jaw.
What are we doing tomorrow? I'm just kidding. But seriously.
And there's any homework handouts everyone's need for spring break.
Yes. I think I gave them out yesterday.
Oh, so we have to do the
It's in here.
You have to do the 8.1.
Yeah, this one here.
Okay.
And I think,
Send me a picture of the rest of 8.1. Yeah, I'll do that.
and 8.2, this is doing board diagrams and Lewis dot diagrams. Have you ever looked at Lewis dot diagrams?
I think so.
Okay, basically Lewis dot is the advanced version of a door. You only look at the outside electrons.
Oh.
So for example, if this is yeah, if oxygen has 2 here, and then that piece has got 600 electrons. It's like that. You ignore the one that's in the middle, so if it's not existing, it's 0. gonna be like that, so it doesn't matter. Yeah, if you were here yesterday, I handed everything up, it was with the no packages.
And can you highlight